Hi, everybody. I'm here to take you through the journey of why Micro Focus selected Pulsar for data ingestion. By way of introductions, my name is Srikanth Natarajan. I'm a fellow and CTO in the IT Operations Management product group at Micro Focus. I've been in the IT operations management industry for many years in various roles, all in engineering, and have worked on various products in the IT ops space, and I led many architecture and engineering transformations. And I'm very, very excited to talk about our journey with Pulsar here. So, we are going to cover the experience that we in the ITOM group in Micro Focus had in both consuming from and contributing to Apache Pulsar, the lessons we learned, and of course, a brief mention about the support from a development partner that we had in our journey as we adopted this technology. So before I get started with the technical aspects of this journey, let me set some context on where is the Micro Focus IT Ops Management and what it is today and why Pulsar was relevant for us. So Micro Focus ITOM has a large portfolio of operations management products, and many of them generate many forms of data on a continuous basis. And our products had a need to process and store a variety of these data in near real time. And the data is primarily, time series, which means, we had a continuously timestamped data, and it is mostly structured, and occasionally it is semi-structured data. And our requirement was that data needed to be processed both while in motion and also while at rest. And at the same time, Micro Focus has Vertica technology, which is really an analytical database used for long-term storage and analytics, but it lacked the streaming engine capability that we needed in front of it to enable real-time transport and analysis of data. So given this context, we had certain technical requirements for our streaming engine. We needed an engine that is enterprise ready as well as SaaS ready. And SaaS ready is particularly relevant for us as we are in the journey to transform our portfolio to SaaS. And then we needed something that was scalable, multi-tenant, had high durability and extensibility, and was easy to productize. Easy to productize in particular was for us important because we are not a project company, we are a product company and a SaaS service company, which means that we develop software once and then of course make it available to many customers. We needed a technology that had observability built in so that we can monitor that in production and take corrective actions as needed. We needed the technology to be support high level of low latency and then high throughput across a variety of data. We needed tiered storage support so that we can basically store data either in depending on the cost of storage, we can store the data at various levels of storage. We needed something which was easier to deploy and operate in production in a container form running in a Kubernetes cluster. And then we did not want to involve any professional services to support the deployment. We wanted it to be done by an end user themselves. And if in SaaS, it should be easy to operate by our SaaS teams. We needed something which was really ready to use, simple to deploy, and easy to operate in both cloud and on-prem. So we looked around for various technologies, and we found Apache Pulsar provided us a great start. Though it did not meet all our requirements of the streaming engine, it did provide us a great start. And then we took that technology, transformed it, and we integrated that with Vertica and created the Microfocus Optic Data Lake. And Optic is Microfocus's platform for IT operations management. You can get more details on it in the reference below. So let me now talk about the architecture of our Optic Data Lake and how the various components of the architecture fit together to accomplish what we needed to accomplish and to meet our requirements. So to begin with, we have various data sources that generate input into our system, either through a mechanism of streaming, which means continuously streaming data, or batch inputs, where data is not continuously sent to us, but sent to us in batches, and those batches are to be stored for long-term storage. So our usage of Apache Pulsar was primarily in the streaming area, leading to long-term storage in Vertica. But I'm explaining the overall needs for us and how different systems were put together to create our data lake. Now, specifically in terms of this session, basically we have spent a significant amount of our resources in this architecture of integrating Apache Pulsar with Vertica. So data comes in streaming through various sources, and then through the Pulsar's brokering and storage systems, we would basically transport that data over, either processing the data for any kind of calculations before the data is persisted, like preparing for baseline determination, preparing for forecasting determination. And then we store the data in Vertica. Now, once the data is stored in Vertica, we also process the data at rest, because we have a lot of post-processing needs, for example, aggregate calculations or long-term, basically any kind of transformations that we need to do. That's the fundamental architecture, essentially Pulsar, our transformation, and then we have some API services that are used by our products that are used both to interface with Pulsar for any real-time subscriptions, or for getting data out of Vertica for any UI or other analysis needs. Now, the significant investment we made outside of putting the system together is to essentially also create containerized services that run in a Kubernetes cluster, so that we can take the benefits of the container orchestration engine to scale the system and to ensure that we can be resilient to changes in the environment, resilient to running in the cloud, and these kinds of flexible environments. So that was a key part of our architecture as well. So let me talk a little bit more about how we ingest data into Vertica and what actually happens there because that is a key part of our innovation on top of adopting adopting Pulsar, containerizing that, and then integrating with our pre-processing solutions. So this is a very key part of innovation we did, which is because we have two systems. There is a streaming system in Apache Pulsar. There is a long-term storage system, which is Vertica, which is a columnar database with some significant support to consume data coming from streaming sources. There is, because these systems have different backgrounds, there was a difference in terms of throughputs and processing and how messages are consumed and stored, etc. So we had to find a system that will actually bring these two together in a way while keeping the data in a way that makes latency low and keeps the data flowing continuously. So to achieve that, we created this microservice architecture where our clients basically indicate to our system about an interest to send the data on a certain topic, which may be an IT operations management topic, through an internal API. Now, that API internally converts into a registration mechanism and registers a topic inside Pulsar through the Pulsar proxy interface. Now, this signals to the system that we are ready to accept messages on these topics coming from the various data sources. Now, as we do this, there is a side effect in terms of basically creating tables in the database in Vertica so that Vertica knows what topic to listen to and then what are the tables to populate the data into. Once that is done, our administration interface also pushes the configuration into what we call as a Vertica Scheduler service. The Vertica Scheduler service is something I'll talk about more in depth in the next slide. Is a service that schedules what are called copy jobs in Vertica. So fundamentally, the problem we are trying to solve is get the backlog of messages in Pulsar and then make sure that those backlogs are processed in time, and then the data is transported over to Vertica and stored for long-term storage. So that is a fundamental job of interaction between Pulsar and Vertica. So we spent a lot of our effort and energy in ensuring that there is a reliable way and guaranteed way that messages are moving and stored in Vertica. And once the invocation of copy command occurs via the Vertica scheduler, Vertica will automatically read messages from Pulsar and store it. So the copy command invocation is a signal to Vertica to go and read messages from Pulsar and persist it. And finally, when the load is done, the load status of the copy command will be sent back to Vertica scheduler so that the Vertica scheduler can go ahead and update the cursor at which it needs to move so that for the next load, and this process goes on forever. So we spent a significant amount of time in selecting the right interface of Pulsar to work with to achieve this message transport to a table storage. And we tried different kinds of subscription that Pulsar provides, different kinds of consumption interface Pulsar provides. and finally settled on one approach, which I'll talk about next. So if we zoom in into the Vertica Scheduler service that we created, this is a view of what happens in a more zoomed in perspective. So we have various producers that produce the data. So these producers can be interfacing with a receiver service, which is an HTTP interface exposed to our clients. This is our interface to register to send their data, and also to register an interest for transporting data. We also have clients that are directly using the Pulsar clients to follow the Pulsar protocol to interface with the Pulsar message system. So these are two ways by which we ingest messages into our overall Pulsar Vertica ingestion service. So what happens is messages are ingested, and these colors indicate different topics on which messages come, and they come in different orders, obviously, because there is different producers and they are just coming at random order. So the scheduler service for streaming into Pulsar, once it gets the config through the interface, gets the backlog of messages that are present in Pulsar, and then it schedules periodically, and we call it frame by frame. And a frame is a micro batch that is a set of messages. And then it schedules that micro batch copy command into Vertica and asks what are known as user-defined extensions in Vertica to read the messages from Pulsar for a topic. So let me explain more about what we mean by user-defined extensions and the copy commands. So copy command is an interface that Vertica provides, where it says you can copy from a file, you can copy from a stream, you can copy from other sources that Vertica supports. And it understands that when we say copy from a stream like Pulsar, it invokes certain extensions that we create called user-defined extensions. User-defined extensions are Vertica's mechanisms to essentially allow us to extend Vertica and interface with external systems which are streaming data or have data in other forms, and so that they can be persisted into Vertica. So user-defined extensions are essentially our addition to this entire, our major and key addition to this entire architecture, because the user-defined extension ensures synchronization between Pulsar and Vertica. Now, you see that I mentioned about a reader interface a lot here. So it's worth spending a few more minutes on that interface so you understand why we chose reader interface. So essentially, we needed a very, very reliable system to avoid duplication of data into Vertica, while also requiring parallel processing of various topics. And so we looked at the consumer interface, we looked at the reader interface, and there is essentially a big difference between the two. And we chose reader interface because in reader interface, you can specify where on a topic readers begin processing messages. So, and the consumers always begin with the latest unacknowledged message. Readers don't retain data or acknowledge messages. Now, this is very, very important for us because we wanted to make sure that we always start with from where we left off. after the batch was read by our user-defined extensions. So this eliminated our duplicate message problems. It created a level of reliability and consistent behavior, and also provided us the interface of integration between Pulsar and Vertica. So this system is something where we spent, I would say, the maximum amount of effort in creation of our data lake, which is really a combination of the streaming engine and Vertica. Given that differences between the two, without the user-defined extensions, we would not have been able to be successfully created this architecture. Moving on, let me walk through how we actually used the work we did here, and then what is the one use case that we solved using the Pulsar architecture. And this is just one example that I'm going to talk about. There are other examples we have, and I'll just briefly mention about them without delving into the details of these. So as I mentioned that we have various sources. They can come in through HTTP receiver. They can also come in through directly through the Pulsar interface. Now, we have basically event sources. So events are essentially, think of them as well-formed messages in monitoring systems that inform the user about a certain condition that needs to be paid attention to. And many times we get a number of events that needed to be grouped together for analysis. And it also helps the users focus on a problem instead of individual messages. So what we decided to do was basically Pulsar has this concept of connectors, and Flink, Apache Flink is one of the connectors that Pulsar supports. And Flink essentially provides some capabilities to window data and scale out jobs that are in various windows, and windows have keys, and then you can do operations on those windowed messages. So our correlation technology that we added on top of Apache Pulsar essentially leveraged the concept of both the streaming data transport from Pulsar. So data would, for example, come from our event systems into a raw event topic, and the raw event topic was persisted as a raw event in the raw event table, as explained in the previous slide, between Pulsar and Vertica using our UDX, etc. But there is also a copy of that going to Flink. And Flink, in the Flink subsystem, we created additional work objects. Those work objects are what we call as auto event correlation technologies that are proprietary to Micro Focus. Those technologies will look at the events that are coming in, do the correlation processing that we need to do, and persist the results back through Apache Pulsar, or directly, if there is no need for streaming, into what are called the machine learning artifacts in Vertica. And then those machine learning artifacts are referenced later for future use, or used for users to have evidence, etc., or it's an internal state that the system uses. And then the output from the correlation is sent to Pulsar sync connector. Sync connector will publish a message into another topic, which is called the correlated event topic. And the correlated event topic is where we would emit a correlation event after being analyzed and autocorrelated through this pipeline. And then that will go through the channel of the, again, Pulsar to Vertica sync and stored as a correlated event. And the correlated event, there's a copy of that also sent to our event management system for users to visualize and act upon. What I'm trying to convey here is a significant aspect of Apache Pulsar we leveraged, which is not only we get the message bus, the scalability and transport and reliable transport, we also could leverage the extensibility, which was one of the requirements we had for a certain specific job type. We had, in this case, like event correlation. And then we're able to extend the Pulsar with the connector and put the system together and create basically an analytical application on top of Pulsar. So we had good success with this, and we had challenges too, but I think those challenges are to be expected in a project like this. But overall, the system held together well. So overall, what was our results? And then, so basically, in our lab today, we verified that we are able to ingest streams at approximately 100 megabytes per second, or 8.64 terabytes per day, with our default setup of Kubernetes worker nodes. So now that is default, which means standard. We use 3 worker nodes and maybe 3 nodes for Vertica for high availability. And then essentially we simulate significant workloads with variety that we expect to see in production, and so on. So this is something we were able to consistently verify. Of course, we plan to double this in the near future by making more innovations in the UDX area and also tuning things. Now, an important point to mention here is that as we were trying to achieve that level of consistent streaming scalability, we spent a lot of assessing reader versus consumer interface, and that led us to essentially the reader interface, because the results were consistently provable and verifiable with the reader interface for our needs. Now, the architecture is linearly scalable, as you saw, for 2 reasons. So we essentially are we have componentry that is essentially incrementally addable, and each component is capable of processing load. And we have a standard formula we use to measure, to kind of assess how much with every addition of a worker node. So obviously, as we add additional worker nodes, the system will scale linearly, and as you add additional Vertica nodes, the system will scale linearly. So we should be able to support much more in reality. But the tested and verified results is what I've indicated here. So I would be remiss if I don't talk about a key aspect of our work here, which was the support we received from Stream Native. Now, Stream Native worked with us as a development partner while we were developing and contributing on making suggestions to issues we saw in the open source, and the needs we had to run the services in Kubernetes, and also we had some security requirements, etc. So we spent a significant amount of time working with this partner. However, that is not to be construed as issues with the technology. It is really meant to ensure that the way we were using it meets the needs of enterprise or SaaS, as the case may be. So just to give you some examples, and this is not the exhaustive list of everything we achieved with together working with Stream Native. So essentially, across various versions of Flink connectors and Apache Pulsar, some of the issues that we resolved includes for the following. So we observed data loss when using the Pulsar Flink connector, and there were various root causes of this issue. And then, as you saw, that Flink was essential for our event correlation application. So we worked with Stream Native to get those issues resolved. But suffice to say that this is an area that will need ongoing support and improvement, both from the community and us, and so something to watch. We had thread leaks in the Flink connector that we got resolution for, and obviously that has issues in terms of resources and resource leakage. Another issue observed in the Flink connector was if a topic is recreated, the connector stops streaming the data. And similarly, when a system breaks down and we restore it back in a DR or a backup restore scenario, streaming stops. So that was another issue that we worked with Stream Native to get it addressed. And of course, we have an internal security and automation testing called STAT, and we get all these issues fixed. And then we got few null pointer exceptions in the connector. Those were resolved. And I'm mentioning this to you mainly to say that be aware of these things as with any new development project. There will be issues, but we could successfully resolve them working with Stream Native. And they have been a good partner providing additional help and tools in terms of, we had a need to dynamically link libraries with our UDX for Vertica, because the Vertica UDX is a C++ library, and that is a Pulsar client as well. So we needed dynamic loading of that and linking of that. And then we needed support for multiple certificate authority support in Pulsar to ensure that our security tests are passed and our TLS behavior works as expected. We needed some help in computing how much storage we needed in Pulsar itself, given the ingestion rates we have, because there were various subsystems in Pulsar, like the bookkeeper and the ledger and other things that use storage. So we needed a way to calculate so that we can recommend to our engineering teams how to size the systems correctly. And then, of course, we worked with them a lot in tuning the various subsystems for both the cloud and on-prem deployment. And then, of course, Stream Native helped to migrate from Flink 1.9 to 1.11. So overall, a good experience, and we're working with Stream Native and also, releasing our technology on time. We continue to work with them for our future needs. So there are some open issues that we still have with this technology that I just wanted to highlight. And I would say that we get occasionally null pointer exception in broker, and we are still validating the fix that has been provided. We are basically having an issue with Flink connector, 2.4.28.4 when we try to back up and restore the data that has been backed up earlier. Then we have an enhancement request pending, which is basically For geo replication, there is a need for different TLS certificate configuration. And then CJ from Stream Native has already raised a pull request for it. So that's something we are glad to check out. So the reference below is an internal reference that talks about the defect that we have. So that concludes my presentation, and the journey we went through, going through the adoption of Pulsar and making it work with the Vertica to create the data lake. I'm very thankful for your attention, and please do not hesitate to reach out